Hello, my crypto friends. Today we're gonna discuss what happened on June 5th, 2018. So in the Ethereum network. So the critical consensus vulnerability was discovered in a Parity Ethereum client. And the issue was discovered on a Ropsten test network and resulted in non-valid blocks with unsigned transactions being accepted and treated as valid by other affected Parity Ethereum nodes. As a result, an accidental fork was created as Geth, and other clients rejected these invalid blocks and Parity accepted them. Following discovery, a patch was issued within hours, and the invalid fork was rejected by the larger chain consensus. So in this video, we're going to discuss the implementation issue, EIP86, valid and invalid signature, and exploit example how to craft such transaction and send it out to our own private Ethereum network. So let's go back to the history. EIP86. EIP86 was proposed by Vitalik Buterin. It's a proposal to abstract out the signature methods in Ethereum transactions. This will allow for customization of signatures in the future. In the current protocol, the public key cryptography ECDCA stands for elliptic curve digital signature, and default non-scheme are hard-coded. EIP86 aims to open up signature protocols, allowing for features such as multi-signature wallets, custom signature cryptography, and conditions such as transaction expiration times associated with a signature. However, the decision to implement EIP86 was deferred and never introduced in Go Ethereum. Previous version of Parity, however, did implement handling for this case, but a missing conditional check in the code caused Parity to potentially accept blocks containing missing signature information. This resulted in a fork on Ropsten test network. The code fix to disallow unsigned transactions when EIP86 is disabled can be viewed here. So the Parity team made a great response. They submitted a patch very quickly into the Parity clients and updated everyone who runs the Ethereum networks to update their Parity nodes to 10.6 or 11.3. So in this video, let's set up our own test private network. And for this, we'll need to have a few things. Let me just remove everything. So we have an empty folder, and here I'm gonna create two folders, validator 1 and validator 2. Also, as any Ethereum network, we will need a file called spec.json. So in this example, I'm going to have proof of authority based private Ethereum network with two validators. So I'm going to go to the POA network GitHub repo called POA chain spec just to grab an example of chain spec.json. So here, I'm gonna need a raw file. I'm gonna copy everything, and I'm going to open my editor to paste it here. So here, I'm gonna remove this. It's just like a hard-coded contract address used for consensus. And here, instead of using save contract, we're just gonna have called validator list. It's gonna be our own list of validators. And we also will remove this multi-feature. This is for the easy way to manage hard forks. We don't need that for now. Okay. So I think I'm missing something. Yeah, okay. Okay, and here. Okay, so here we're gonna provide our list of validators who is gonna be validating the network. So let's create our own file. So let me just remove all the contents from this folder. Okay, so I'm going to go to my Ether wallet, and we're gonna create a new account. We're gonna have password POA to the moon. We're gonna download this file. We're going to have we're gonna put it into validator1 folder. So in this folder, I'm gonna create a folder called keys, and inside of this folder, we're gonna have this name, core. So it has to be core, and then we're gonna put it here. Actually, let's rename our network called testnet. And then we need to rename this one as well, testnet. Okay, so we have this address, and we need to also create a password that we created. I'm gonna create it, not password. And we specified POA to the moon. So, and we need to grab the address. This is the address from our key store file. So I'm gonna put this address here, and we're gonna prepend 0x in the beginning. And the second validator, let's create a second validator, private key, POA to the moon. And we're also gonna download that file and put it into the validator2 folder. So here I'm gonna do the same thing, create a folder keys. Actually, yeah, and then testnet. I'm gonna put this file into here. So now we have our spec.json, we have our password, and now we need to create two configuration files for our nodes. So it's gonna be called node.toml. So the example could be found, I will provide my own repo, and I think we also have it here somewhere. No, we don't. I thought we did. So yeah, we can just have our own spec.json that I think I have here. Okay, I'm gonna explain everything that is happening. So in our spec.json, we need to specify a path to our spec.json file, and we need to specify which folder will be used for blockchain synchronization. So it's going to be called Parity data, and we need to move this folder into the Parity data keys folder. Our network port 30303 and RPC port 8511, some of the APIs. So we need to specify our path to our node, that password file, and the account which is used here. So I'm gonna replace this address here. Then we specify that we are gonna be a miner, and we're gonna be mining with this key. And that's about it. And I'm gonna copy the same thing and do the same thing for validator 2. So again, we need to specify different ports, just not to conflict. And we need to specify a different address as well. So, and that's about it. So, no, not yet. So we need to also create a folder called Parity data. And I'm gonna move my keys folder into that folder. So now our setup is ready. So let's start mining the network. So here, I think I'm gonna split this into, Okay, let's do it like this. And then, okay, let me increase it. So now I'm gonna go to my validator1 folder. So I'll need two versions of Parity. So the first one that I have globally installed is 10.4, which has a bug in it. And the other one that I have is, that I also installed, is 10.6. So one validator will be running software with a bug in it, and then the second validator is going to run updated Parity node. So what I need to say is the parity dash config not tomo net none equals none and no UI. If we've done everything correctly, it should run. And then we need to copy this public node URL. So we can see the first validator already started working and he started mining the network. And I'll need to do one more thing here. Is inside of validator 2, we need to say something like, let me look it up pretty quick. Second validator, not that tomo. So here, yes, so we need to add those two lines. Discovery true and reserve peers equals boot nodes.txt. So we need to provide a way to connect to the second validator to the first validator, so they can be, so it can start synchronizing the chain and both participating in the consensus to mine the network. So boot nodes.txt, and the value I need is this value, public node URL. And I'm gonna save it here. So now we can see we already created 16 blocks, and I'm gonna run the second validator node, and it should synchronize the chain. So I'm gonna do the same thing with a newer version of Parity, config node tomo. Okay, yeah, okay, I know what I forgot. It basically says the WebSockets port is busy. So I'm gonna look at here, and I'm gonna disable the WebSockets port on my second validator node. WebSockets disabled equals true. So now I can run this again, and I should see the synchronization happening to make sure, okay, yeah. So now we can see that we are successfully launched our private Ethereum network, and we are participating in consensus by mining our own chain. So the next step is to create an exploit, the most interesting part of this tutorial. So I'm going to create a file called exploit.js, and here we need a terminal. Actually, let's create a folder called exploit. Actually, yeah. So let's create a folder exploit. And in this folder, I'm gonna initialize the npm repository, because we'll need a one dependency called Ethereum.js tx, and I'm gonna save it here. So as soon as it's installed and downloaded, I'm gonna create a file called exploit.js. So in here, I'm gonna look at my previous example that I created before, and basically I'm gonna walk you through this example. So here we have this module imported. We need to specify our chain ID. So So we need to specify a chain ID for our network. So in our spec.json, we copied it over from POA network core, which is the chain ID 99, or in a hex value, it's 0x63. So I need to specify the same chain ID 99. Then we are gonna craft our transaction. So we're gonna say we want a transaction with non-zero, gas price 0, gas limit something. So the reason why I'm specifying gas price 0 is because we need to, if I specify some gas price, it's going to create a transaction from 0xFFFFF address, which doesn't have any money in it. So the transaction will be rejected. For your example, you can send some money to that account. So in order like the gas price, if you want to test it with a gas price. But for our purposes, we're just going to set it to 0. And our miners, they are accepting free transactions. As you can see, minimum gas price equals 0. So some gas limit, some address to send, some transaction to, some value 0, data 0. And this is the most interesting part. So we're basically saying we don't have any signature generated. It's just going to be a 0 and 0. So that's what it means, unsigned transactions. It doesn't have any valid cryptographic signature. So, and then we're gonna just run this exploit, and it gave us the RLP encoded signature to send to Ethereum network. So here, and now I need to send this transaction to our network and see what's gonna happen. So for these purposes, I'm gonna use the JSON RPC API, and I'm gonna craft this transaction. So I'm gonna put it here. See, ETH central transaction method, and we need to specify our node port, our port 8511. So here I'm going to stop the node that has the valid consensus. I mean the valid, the patched fix, to make sure this node is not going to receive this transaction, because if it receives that, it will reject it. So now we're going to send this to our node, and here we go, success. We send this transaction, we got our transaction hash, meaning the transaction is valid. Here is your transaction hash, and we can see this transaction was just included into 89 block. So now, if I'm going to run the second node again, the consensus will be broken. This node will synchronize the chain until block 89, and then it will start mining its own network, because the block 89 is not valid. So let's see. We run on node again, and here we go. It gives us the error message saying the stage 1 block verification failed for this particular block. Actually, it was block 90, E5C5, and we cannot accept such chains, so it will start generating its own blocks, and it's not going to include that block. So meaning we just going to have the chain split. Same thing that happened to like Ethereum and Ethereum Classic. The consensus was not an agreement, so now we have two different chains. Yeah, that's about it. Thank you for watching. I was just wondering like why it's not creating its own blocks, and I realized I made one mistake, that we only have one validator in our list. So if we include the second validator in our spec.json, and if we recreate the network, like I'm gonna remove all the data from both from both validator 1 and validator 2 and just start the new network again. You're gonna see the actual chain split, because we were running the second node just as a regular node, not as a mining node. That's why we didn't see new blocks popping up. So now I'm gonna run this again. I'm gonna make sure the E node is valid one. So good nodes. Okay. And here I'm gonna run the second node to make sure they're gonna have, okay, now I can see that this node is also mining the network and this node is also mining the network. If we turn this off, this will continue to create blocks if this node is offline. And so we saw that it created 2 blocks, and if we start that node, it will synchronize those 2 blocks and continue mining all together. Yeah, so it's all good. So now let's create our exploit again. I mean, let's send this exploit to our node. Okay. Oops, we forgot to turn that off. Let's see who mined it. Okay, that node is mined. That transaction that we're just now gonna see that the chain split again, and we're gonna see they're not gonna be mining same chain. They're gonna have 2 different chains. Since the block 11, so now this node is gonna create its own block 12. See, the hashes are different for block 12 here and here. That's the good example of the chain split. They're not in consensus. They're creating their own blocks. And to verify that, we also can run one more check, is JSON RPC call, JSON RPC Ethereum get transaction by hash. So if we send this request, you're gonna see that the transaction that was mined is invalid, in fact. So get transaction by hash, okay. So I'm gonna copy this example and put it in here. I'm gonna take this transaction hash and insert it there. And now we only need to add a content type. Okay, we need to add this data. Okay, and for the pretty output, okay, so we just send this request to our first node saying, okay, give me the transaction data for this hash. And we can see the full transaction data, that it actually has a transaction from this weird system address. It doesn't have any signatures, RNS, but it's there, it's in a block, it has a block number. So yeah, now we have demonstrated you the hack, the exploit, the chain split. So hopefully now you have better understanding what is the actual fork in Ethereum, what is consensus, and why is it important to have the same consensus, so to prevent any chain splits. Thank you very much for watching. Have a good day.